Physics is the most powerful tool humans have ever created to understand reality. It can describe atoms. It can predict black holes. It can trace the universe back to its earliest moment. Yet there is a strange gap hiding inside this success. The more we learn, the more one question refuses to disappear. Why does any of this exist at all? This is where everything becomes uncomfortable, because physics is not just another subject. It is the foundation of modern knowledge. It explains motion, time, energy, and the structure of space itself. It builds the equations that power our technology and our understanding of the cosmos. But even with all of this power, physics may still be unable to answer the simplest question of all. Why is there something instead of nothing? This tension sits at the center of one of the most profound debates in science and philosophy. If physics can explain everything that happens inside the universe, then does that mean it can explain the universe itself? Or does the universe contain something that sits beyond explanation? Scientists like Brian Greene argue that physics is becoming more complete with time. We are no longer guessing. We are writing precise mathematical laws that describe reality with extreme accuracy. Quantum mechanics explains the behavior of particles at the smallest scale. General relativity explains gravity and the structure of space and time. Together, they form a picture of a universe that looks increasingly like a unified system of rules. But there is a hidden problem inside this success. Every new discovery explains how something works, but it does not always explain why those rules exist in the first place. It is one thing to describe the behavior of reality. It is another thing entirely to explain the origin of the behavior itself. This is where the question begins to shift. Because once physics becomes complete in describing everything that happens, a deeper question appears in the background. Why does mathematics describe the universe so perfectly? Why do these specific laws exist and not others? And why is there a system of laws at all instead of pure nothingness? Most people never realize how radical this question is. In everyday life, it feels natural that things exist. But in physics, existence is not guaranteed. Theories describe possible universes with different laws, different constants, and different outcomes. In some models, even space and time behave differently. This suggests that the universe we live in is only one possibility among many. Yet we still do not know why this particular possibility is real. This is where the idea of limits begins to emerge. Physics depends on observation. It depends on measurement. It depends on what the universe allows us to see. But there are regions of reality that may never be observable. The earliest moment of the universe, before the laws of physics as we know them fully existed, is still hidden behind a barrier. Some theories suggest a multiverse with regions forever beyond our reach. Others suggest that space and time themselves break down at fundamental levels where no experiment can go. So a difficult question appears. If something cannot be measured, can physics ever truly describe it? And if physics cannot describe it, does it mean it does not belong to science, or does it mean science has reached its boundary? This is where Brian Greene and other physicists walk a careful line. They do not reject the idea of deeper explanation. In fact, they search for it. The goal of modern theoretical physics is often described as a theory of everything, a single framework that could explain all forces, all particles, and all interactions in the universe. If such a theory is found, it would represent one of the greatest achievements in human history. But even that raises a new and unsettling question. If a final equation explains everything that happens, then why does that equation exist? Why that structure instead of another? At that point, explanation begins to loop back on itself. This is where the discussion becomes more than science. It becomes a question about the limits of understanding itself. It challenges the idea that every question has a physical answer. It suggests that some layers of reality may always remain just out of reach, not because science is weak, but because the structure of reality itself may not allow complete explanation. In this video, we will explore this boundary. We will look at what physics can truly explain, where it begins to struggle, and why the deepest question of existence may not behave like a normal scientific problem. We will also examine why some scientists believe that even a complete theory of physics may never answer the question of ultimate origin. This is not about proving or disproving belief. It is about something more fundamental. It is about the limits of knowledge itself and whether the universe is fully explainable or only partially knowable from within. You are watching a space where science meets its own horizon. Welcome to the channel. If you enjoy exploring the deepest mysteries of the universe with clarity and curiosity, make sure to subscribe. Physics is often treated like the final answer to everything. It is not. It is a description system. It tells us how things behave with extreme precision, but it does not always explain why those things exist in the first place. At its core, physics is about patterns. It looks at repeating behavior in nature and turns that behavior into mathematical rules. When an object falls, physics does not say the object wants to fall. It describes the force of gravity and the curvature of space that produces the motion. When light bends near a star, physics does not assign intention. It describes how mass affects space-time and how light follows that geometry. This ability to describe behavior is one of the most successful achievements in human history. Gravity was once a mystery that felt almost spiritual. Now it is explained through general relativity, where massive objects bend the fabric of space-time itself. Time does not flow the same everywhere. Near strong gravity, time slows down. This is not theory in a loose sense. It has been measured using atomic clocks placed at different heights on Earth. Motion itself has been broken down into precise laws since Newton. Objects continue in motion unless acted on by a force. That simple rule explains everything from planets orbiting stars to rockets leaving Earth. Even though Newtonian physics is not complete, it still works in most everyday conditions with stunning accuracy. At the smallest scale, quantum mechanics takes over. Here, reality behaves in ways that seem almost impossible from a classical point of view. Particles do not exist in a single state until they are measured. They exist in probabilities. These probabilities are not guesses. They are calculated with extreme precision and confirmed through experiments that match predictions to many decimal places. Even the structure of the universe itself is described by physics. Cosmology explains how the universe expanded from a hot, dense state into galaxies, stars, and planets. It describes cosmic microwave background radiation, a faint signal still present today, which is considered one of the strongest pieces of evidence for the early universe model. Across all these scales, physics performs something remarkable. It reduces complexity into equations. It turns chaos into structure. It allows predictions that can reach into the future and into the distant past. But something important sits beneath all of this success. Physics describes how systems evolve once they exist. It does not clearly explain why the systems exist at all. It can describe gravity, but not why there is a universe that contains gravity. It can describe quantum fields, but not why those fields exist in the first place. This is where the limit begins to appear. The language of physics is built on relationships. One quantity depends on another. One force interacts with another force. But the language itself does not fully explain the origin of the system it describes. There is also a deeper issue hidden inside modern theory. The laws of physics appear constant across the observable universe. Light behaves the same in distant galaxies as it does on Earth. The electron has the same properties everywhere we have observed. This uniformity allows science to function. But it also raises a silent question. Why is reality so consistent in the first place? Even more unusual is the fact that the universe seems to be fine-tuned for structure. Small changes in physical constants would make stars impossible or prevent atoms from forming. This is not widely obvious outside scientific discussion, but it is a known feature of cosmology. The values of fundamental constants sit in a narrow range that allows complexity to exist. Physics can measure these constants with high precision. It can use them to predict outcomes, but it does not explain why these exact numbers exist rather than others. So physics continues to grow as a tool of description. It becomes sharper, deeper, and more unified. Yet its success highlights a boundary. It tells us more and more about how reality behaves, while leaving open the question of why reality behaves at all. Physics has never been satisfied with partial answers. Every time a new layer of reality is discovered, the goal becomes to unify it with everything else. The dream is a single framework that explains all forces of nature in one consistent system. Right now, physics is split into two powerful but separate descriptions. One governs the very large. General relativity explains gravity, stars, galaxies, and the structure of space-time itself. The other governs the very small. Quantum mechanics explains particles, fields, and the strange behavior of matter at microscopic scales. Both theories work extremely well. Both have been tested with extreme precision, yet they do not fully agree with each other. This disagreement becomes most visible in extreme environments. Inside black holes, gravity becomes incredibly strong while quantum effects also become important. At that point, both theories begin to break down. The equations no longer fit together in a clean way. This is one of the deepest problems in modern physics. To solve this, scientists have searched for something more fundamental. One of the most famous attempts is string theory. Instead of treating particles as tiny points, string theory suggests that everything is made of tiny vibrating strings. Different vibrations create different particles. In theory, this could unify all forces, including gravity, into a single framework. Another approach is quantum gravity, which tries to directly combine quantum mechanics with space-time itself. Loop quantum gravity, for example, suggests that space may not be smooth and continuous. Instead, it may be made of tiny discrete units, like a fabric woven from individual loops. These ideas are mathematically powerful. They attempt to reduce all physical laws into one underlying structure. If one of these approaches is correct, it could mean that every event in the universe, from the formation of galaxies to the decay of a single particle, follows from one set of equations. This possibility is both exciting and unsettling. It suggests a universe that is completely rule-based. No randomness without structure. No event outside of law. Everything connected through a single system of logic. But here is where a deeper question appears. Even if such a theory is found, it does not necessarily end the mystery. It only shifts it, because a perfect equation would still exist. It would still have a structure. It would still contain specific rules rather than others. And that leads to a strange problem. Why does that equation exist in the first place? This question is not about how the equation works. It is about why there is an equation at all. Physics can describe how one part of the system leads to another part. It can show how forces interact and how particles evolve, but the existence of the entire framework itself becomes harder to explain using the framework it produces. There is also a hidden assumption in all of physics. The assumption is that reality is mathematical at its core. This idea has been incredibly successful. Equations predict planetary motion, particle collisions, and even the expansion of the universe with high accuracy. Yet there is no guarantee that mathematics must describe reality in the first place. Some physicists quietly point out this gap. Even if a final theory is found, it may describe everything inside the universe, but not the reason the universe has that structure. The theory would be complete in behavior, but silent on origin. So the search for a theory of everything continues with confidence and precision. Yet underneath the mathematical progress, a deeper tension remains. The more complete the laws become, the more they seem to point beyond themselves toward a question they cannot fully contain. Science is built on one strict rule. Only what can be observed can be known. Every law of physics, every theory, every discovery depends on measurement. If something cannot be tested, it cannot become part of scientific knowledge. This is what makes physics powerful. It removes guesswork. It removes belief. It replaces uncertainty with data. But this strength also creates a boundary, because the universe may contain things that cannot be observed directly, no matter how advanced technology becomes. One of the biggest limits appears when we try to look back to the beginning. The Big Bang Theory describes the expansion of the universe from an extremely hot and dense state. Evidence for this includes cosmic microwave background radiation, a faint glow spread across the entire sky. This signal is one of the oldest pieces of information we can observe. It tells us how the universe looked when it was only a few 100,000 years old. But there is a point before this where observation breaks down. Earlier than that, the universe becomes opaque to our measurements. The laws of physics as we know them begin to lose clarity. Time itself may not behave in the way we expect. We can build mathematical models of this early period, but we cannot directly test what happened at the exact starting moment. Then there is the idea of regions beyond what we can ever see. The universe is expanding. Light from distant regions may never reach us, no matter how long we wait. This creates a cosmic horizon. Beyond it, there could be vast structures, galaxies, and even different physical conditions. But they are permanently outside observational reach. Some theories go further and suggest a multiverse. In this idea, our universe is just one bubble among many. Each bubble could have different physical laws, different constants, and different outcomes. But if other universes exist outside our own, they would not interact with us. That means they would also remain unobservable. Physics could describe them mathematically, but it could not confirm them experimentally. Even within our own universe, there is another mystery that resists full explanation. Consciousness. We can measure brain activity. We can track neural signals. We can correlate thoughts with physical processes. But the direct experience of awareness remains deeply difficult to reduce into equations. It is described from the outside, but not fully captured from the inside. This leads to a deeper issue. Science does not just require existence, it requires access. If something cannot be measured in any way, then physics has no method to confirm or reject it. It may be real, it may not be real. From the perspective of science, the result is the same: silence. This is not a failure of science. It is part of its structure. Physics is limited by interaction. It can only study what leaves a trace. It can only analyze what produces data. If a phenomenon never produces measurable effects, it stays outside the reach of scientific tools. This creates a subtle but important consequence. Knowledge is not only about what exists, it is also about what can be observed from within the system. The universe may contain layers of reality that are fully real, yet permanently hidden behind the limits of observation. So as physics expands its reach into deeper scales of space and time, it also meets boundaries that are not technological, but fundamental. Boundaries defined not by lack of effort, but by the structure of observation itself. Physics is extremely powerful when it comes to explaining how things happen. It describes motion, forces, energy, and time with precision that no other system can match. But there is a different kind of question that keeps appearing, and physics does not handle it in the same way. The question is why? Why does gravity exist? Why do particles have mass? Why do the laws of nature take the form they do? These are not questions about behavior. They are questions about origin. And physics begins to struggle when it moves in this direction. Every explanation in physics relies on something deeper. Gravity is explained by general relativity, but general relativity is based on space-time geometry. Quantum mechanics explains particles, but it is based on mathematical rules that are assumed rather than derived. Each layer of explanation depends on another layer underneath it. This creates a chain of reasoning that never naturally ends. One law explains another law, which depends on a deeper structure, which again depends on something else. Even the most advanced theories do not break this pattern. They extend it. This is why some physicists quietly point out a strange loop. If every explanation requires a deeper explanation, then at some point the chain must either stop or become circular. But physics does not show where that's stopping. Point is, the question becomes sharper when applied to the universe itself. Why do any laws exist at all? It is possible to describe a universe governed by different rules. Mathematics allows endless possibilities. Universes with different constants. Universes with no gravity. Universes where matter cannot form stable structures. Yet only one set of rules appears to exist in reality. Physics can describe how these rules behave. It can calculate outcomes with extreme accuracy. But it does not explain why this particular set of rules exists rather than another. The selection of the laws themselves remains outside the system they define. This leads to a deeper philosophical boundary. One possibility is that reality is self-contained. The laws exist simply because they exist. There is no deeper reason behind them. They are fundamental, and explanation stops there. Another possibility is that explanation requires something beyond physics, something that is not part of space, time, or energy, something that is not limited by physical laws. But if such a thing exists, it is not something that current physics can directly describe or test. This creates a tension that cannot be easily removed. Physics assumes that every effect has a cause within the system. But the existence of the system itself does not clearly fit into that structure. The tools used to explain reality are built inside reality. They cannot easily step outside it. There is also a subtle point that often goes unnoticed. Asking why assumes that reality must have a reason in the same way events inside reality have reasons. But that assumption may not always hold. The structure of explanation itself may break when applied to the totality of existence. So the boundary begins to appear clearly. Physics can describe patterns with extraordinary depth. It can trace how systems evolve from one state to another. But when the question turns toward the existence of the framework itself, the language starts to lose its grounding. At that point, the question of why anything exists may no longer behave like a scientific problem. It may belong to a different category of inquiry, one that physics can approach but may never fully contain within its equations. The word God carries many meanings across history, culture, and belief. In this discussion, it is not being used as a simple religious claim. It is being used in a deeper sense. The idea of an ultimate cause, the foundation of existence, the source of all physical laws, space, and time. Physics does not directly address this idea. It describes structure. It describes behavior. It describes relationships between energy, matter, and space-time. It can map the universe with extreme precision down to particles that exist for fractions of a second, but it does not assign purpose to those structures. A law of physics can explain how a star forms from collapsing gas. It can explain how nuclear fusion produces light and heat. It can even predict how long a star will live. But it does not explain why stars exist in a universe where they are possible in the first place. It does not explain whether their existence has meaning or intention behind it. This is where the limits of language begin to appear. Physics is built on mathematics. Mathematics is built on logical relationships. These tools are powerful because they are precise, but they are also limited by what they can express. They describe patterns, not purpose. There is a lesser-known idea in modern physics called mathematical realism. It suggests that the universe is not just described by mathematics. It is mathematics. In this view, physical reality and mathematical structure are the same thing. There is no separation between the equation and the existence of the equation. If this idea is correct, then the boundary between physics and deeper meaning becomes unclear. It would mean that reality is not something written in mathematics. It would be mathematics itself, existing as a complete structure. But this leads to another difficult question. If reality is purely mathematical, then why does this mathematical structure exist instead of another? Mathematics allows infinite possible structures, yet only one appears to correspond to our universe. This returns the discussion to the question of selection. Why this structure? Why this set of rules? Why this existence? On the other side, if reality is not purely mathematical, then physics may be describing only a surface layer. It would mean that equations are tools used by human minds to interpret patterns, not the full essence of existence itself. In that case, there could be aspects of reality that are not reducible to formulas or numbers. This is where the debate becomes deeply divided. Some scientists see physics as approaching a complete description of everything that exists. Others see physics as inherently limited because it operates within the system it is trying to describe. It cannot easily step outside and observe the foundation from which it arises. The idea of intention or purpose adds another layer of difficulty. Physics does not include intention as a variable. It does not require purpose to function. Equations remain valid regardless of meaning. A particle behaves the same whether or not there is any reason behind its existence. This makes physics extremely effective at prediction, but silent on meaning. So attention remains at the center of this discussion. Either reality is fully self-contained and describable through mathematics alone, or there is something beyond description that gives rise to the structure in the first place. In both cases, the tools used to study reality are still operating from within it. This brings the question back to its core. Whether reality is something discovered as an external object with fixed properties or something interpreted through tools that may never fully escape their own limitations. Physics has taken humanity further than any other way. Thinking, it has revealed the structure of atoms, the behavior of light, the shape of space-time, and the history of the universe itself. It has turned mystery into measurement and chaos into order. Yet even with all of this progress, something important still remains out of reach. The most powerful feature of physics is its ability to describe how reality works. But description is not always explanation. A complete set of equations can show how everything evolves, how every force interacts, and how every particle moves through space and time. Still, those equations do not clearly answer why they exist in the first place. This is where the central tension remains. The universe may be fully describable in mathematical form, down to its smallest detail. Every event may follow from deeper laws. Every structure may emerge from consistent rules. Yet none of that guarantees an answer to the deeper question behind it all. Why those laws? Why that structure? Why anything exists instead of nothing? Across all of physics, from cosmology to quantum theory, there is a repeating pattern. Each discovery expands understanding of how the universe behaves. But each discovery also reveals a new layer underneath it, a deeper rule, a more fundamental structure. And with every step downward, the question of origin becomes harder to contain inside the system itself. This is why the boundary between science and the unknown does not feel like a sharp line. It feels like a horizon, something that moves forward as knowledge grows, always staying just ahead of what can be fully reached. Physics can approach it. It can describe it. It can get closer with every new theory, but it may never fully cross into the space where the final answer sits. And that leaves a quiet but powerful thought behind. The universe might not be incomplete. Our understanding of it might be, or the question itself may belong to a kind of reality that cannot be fully captured by the tools we use to study it. Either way, the search does not end. It only deepens. If you enjoyed exploring these ideas, take a moment to like the video and subscribe to the channel. There is much more to uncover about the universe, and each question leads to another layer waiting just beyond what is known.